Um, Today we're going to talk a little bit more about assemblies. That's why I brought some piping systems, for example, and talk about other things that you need to think about in terms of using materials. You can have the greatest material possible, like this copper pipe will last very long, but if it's connected in a joint that's not done properly, it can pull out. And half-inch pipes are the smallest common pipes in buildings, but when it's fully open with the supply pressure, it creates a lot of water damage very quickly. A lot more than if it's just a little drip. So pull out has a lot more consequences. So we'll talk a little bit about soldering. So I'll pass those around because you can see, I call those socket joints. They have all sorts of names, but the idea is you put one pipe on top of the other, and then by capillarity you have the solder coming into it. So you got a main joint that actually went through service, and then you have two parts to look at. So we'll do plumbing systems. We'll also go back to some building structures. We'll talk about roof joists, which may be a good topic this year. We're getting a lot of snow, so we may soon hear in the news that schools have to close because of snow load and those sorts of things, because it's always, all buildings are built with a certain number of pounds per square foot, and then when you exceed it, it's mostly dependent on the quality of your welded joints on the joist, whether you're going to be able to sustain additional load. I have a automotive suspension example that I want to bring up. We'll talk about requirements in oil and gas and aerospace. It's going to be a busy lecture today. Quality control or quality assurance. One way to think about it, if I say quality control, a lot of times I'm referring to checks that are done during fabrication. If I'm talking about quality assurance, a lot of times are checks that are done after the fabrication. So if you have something critical, say you have something built in China, and you want to make sure when it comes in that it meets all your requirements, you can enforce them to do a good quality control so the assemblies don't get shipped for no good reason. And when they come in, you do a receiving inspection. So you go through it again, essentially a second set of eye, trying to see if you could find something. It's not, in the dictionary, but it's the way that I've been used to think about it. Lots of times, the contractor or the fabricator is left with the main responsibility for inspection. It's not always the case, but if you remember in the first class, I brought the welding code, and what the welding code says is the fabricator needs to do 100% visual inspection. There's nothing else that is required. So after the welding contractor is done with the installation, the other guys can come and put the insulation. There's nobody else by law or by basic contracts that is supposed to come and say, oh yeah, these welds are good. So it's important to know, because you can always ask for more. If you're building something that is critical, like in aerospace, they always have different levels of quality control from the time that the part is built, from the time that it's in assembly. It's a very continuous process. There's a difference between doing a quality control and the material. Remember, we had our chemistry requirement, we had mechanical testing by ASTM. When you start to talk about an assembly, I mentioned about all-terrain vehicles. These are little four-wheelers, four-wheel drive. You can go in the woods, in the snow, and have fun. There are not that many industry requirements on how to assemble, how to design these units. Even cars, there's a lot of flexibility that is left to the car manufacturer. But the bottom line is they don't want have a failure because bolts were not put on and basic stuff like that. And what happens in terms of how they organize their production, even for ATVs nowadays, their tooling is set up so there's a very specific sequence for torquing bolts. And if they don't follow that sequence, they need to ask the supervisor to come and reset the tool program. So if they're supposed to go through 5 bolts, half an inch, they got 5 shots to do that, and then 2 shots to do larger bolts, and then it goes on and on and on and on. So the likelihood of them not screwing a fastener or a set of fastener is, by far reduced. Plus, they get provided with the exact number of bolts they need for each project. That's done a lot also in little medical devices. When I came with my little probe and stuff, they have a tray. This is what you're supposed to use. And if you have extra parts, there's a problem. So they can always go back in the chain of fabrication and say, okay, you missed out these 2 bolts on the unit before. Now we have to go back and put them back on. So it's a way in terms of quality control, so that when it's all fabricated, you don't try to bend yourself all over and see if all the bolts are there. I bet that's the intent, that you can just so hardly make a mistake that when it's all said and done, you don't have to go back and look for nuts and bolts everywhere. Completed product. I put it as quality control. One example is all the pressure vessel systems. A lot of them are subjected to a slightly overload, a proof load in terms of pressure. So you fill it with water or fluid, then you over pressurize them, make sure they don't leak. Because a pressure vessel has the main assembly. A lot of times it's got little pipes and nipples coming into it. It's got a lot of welding. If you don't want any leak when it gets to be at the installation site, the proof load test will tell you all about it. Same for those pipe that I'm passing around. There is a requirement in most building specification, that the plumbing contractor energize the system and have it hold pressure about 50% more than the operating pressure for a good period of time. So if there's any small leak, he can find those. Now, if there's a burst or a pull out of a joint, he fixes it before they go on with putting insulation, drywall, and finishes, flooring, you name it. So it's a system test, and whatever you'll be building in the future, whatever prototype, it could be that it's made out of 100 parts and it's supposed to lift 20 pounds. It's a little vacuum system able to move the chairs or whatever. If that's what you want, 20 pounds, maybe you test it at 40 pounds. And if it's within the design envelope without creating any problem, you could do it on each unit. When they built these ATVs, every single unit gets fired up and goes on a treadmill at the end of the test to make sure that everything is all right. They check the emission, they check everything when it's all said and done. So when it leaves the factory, they know it's going to go and be used without a problem. So going back to the STM here, very specifically for those socket joints that I've been passing around. So you have the pipe here and you have the fitting on top. You have a little clearance. The schematic says it's exaggerated. So this clearance here between the pipe and the fitting is very small, and the only way to get the capillarity to work here is to make sure you don't have too much dirt, that you don't have too much oxidation on the surfaces. So you have to sand them. If anybody has done any soldering, you sand the copper, you sand the fitting and the pipe, you put a flux, then you start heating up. When it starts becoming hot enough, it's where you start adding the soldering material, a low fusion tin alloy generally, and you could use some silver in it. There are a lot of different solders depending if you want a high strength or if you want an easy job to be done. There's a schematic here showing exactly what I was talking about. So you see the grinding marks from the guy who prepared the pipe. You see the flux that's flowing a little bit on the behind side, and this is hot enough so they're starting to bring the filler material here. The joint that I passed around, it's never looks exactly perfect. A lot of times when you see deposit extra solder on the outside, it's not a sign of strain. It's actually a sign that was potentially a little hard to get the solder to penetrate in the joint, and that's why it built up on the outside. So it's not a quality criteria to see a lot of solder on the outside, but if you see a little lip all around, you know that it actually was sucking in. And sometime from the other end, if it's just a linear joint, you can see the solder going all the way to the end of the joint. That's always a good way. The other way, if you remember in the first class, I passed around a sample that was peeled, so you can see if you have coverage or not. But that's part of qualification of the plumbing people. So you can have them make some joints so you know that they can do it right consistently. So if I had the fitting over here on top, just a linear joint. What I want, a lot of times I bring the heat from one side and I'll come here with my filler and just try to get it in, and I'm hoping to cover this whole space. Now, we'll get back to that. The way you cover the space in the STM, they talk about how to cut it, how to get the burrs out, get the corner of the pipe clean, the fluxing, how you assemble, how you heat, and how you clean. So the solder flux has a lot of strong chemicals in it. It's great for etching. It cleans the metal surface, but when it's all said and done, it's a corrosive environment for the pipes. So you have some requirements for cleaning it, and there are also requirements for flushing the inside of the piping so you don't keep these corrosive residues in your plumbing system. If you see, there's not really a procedure for checking quality here. It's just the way this very particular specification is. It doesn't tell you what's good and not good. It says if you follow the procedure, hope for the best. So in the first class example, I was talking about the Copper Development Association. They arrived to a criteria where here, in terms of coverage, you want 70% or more of binding. Binding means that it's really filled between the pipe and the fitting. And it's hard to tell, how each individual plumber will know that or will be able to verify it. But after the fact, if you open up the joint, it's a very quantitative criteria. And it's also very useful. The reason why the CDA had these is to qualify the plumbing installers. They have them make joints of different sizes, see if they know how to do it, and then they can go on to buildings, condominiums, or commercial, residential, and do work that doesn't have to be reworked all the time. That's the bottom line. Because you have a lot of joints in a single plumbing system. Now, I hope I made it sound like it was difficult, because it's difficult. Especially if you're in a building and if it's an existing installation, there's some drywall already in there, and you're there with a torch. You have to be careful with where you put the heat. If there's water in the system, it prevents you from doing repairs by soldering. You have to kill the line, get the water out. Otherwise, it's very hard to heat up the pipes. So I did bring some newer systems that are primarily based on plastic tubings, and then you get some metallic fittings. And the idea here is there's an expansion tool that allows you to expand the pecs here, so it's cross-linked polyethylene. So you can just slide it over these fittings that have barbs, and when the pecs is relaxing back to its original diameter, it forms a very good seal here over these barbs, the high points. And that sleeves here is called the expansion ring. It's actually just an extra stiffener that you put on top, so you expand the two together, and when they come back, it's an additional spring to hold the joint tight. If you think about this, as opposed to having to clean the joint, by brushing it, putting the flux, putting the heat right, and all of that here, as long as you expand it with the tool, push it all the way, and let it go, you got a joint, and they're all going to be the same. So sometimes in terms of use of materials, if you can save yourself some risk or variations between workers by having something that's easier to use, it's worthwhile. So I'll pass those around if you're interested. And as I thread a joint on the large assembly, thread a joint's a little bit the same story. You have to think about, okay, am I going to ask the guys to put some thread tape, Teflon tape, or am I going to ask them to put a certain pipe dope, or I don't remember the technical term, but essentially a semi-rigid, a goop that allows you to get a little bit more lubrication when you tighten threaded joints. Joint compound would be the proper term. So that joint compound, who knows who's going to put it on, how much they're going to put from one time to the other, and how much they're going to torque the joint, one pipe with respect to the other. So there's just a lot of variables. It's okay, but if you have a guy on the job, Armford has been talking to you about, fusion welding and the details of the metallurgy and all of that. I also, if you remember, mentioned about different welding processes in the first week of class. I said you can use a stick, you have semi-automated processes. So this was done using semi-automated processes. And as you can see here, well, I don't know if you see it, but I see that it's relatively convex. So it looks like they've thrown metal in that corner. The corner is hard to weld. So if I have the lower core, it's actually an empty tube, just like this. And then I have the solid bar that runs. So we're looking here at the joist going this way. The solid bar runs parallel to it, and then it goes on a diagonal. So what we're looking at, what I'm seeing in that image, and I'll image here, is a big chunk of welded metal. It's a little hard for you to say because it's painted, but if you were in the factory and you see this is a no, no, no. Because what it means is they were trying to go too fast. They were bringing in a lot of filler metal, but not heating enough the base materials. Lack of fusion. And there are a few problems in terms of basic welding requirements. There's one here, they have an overlap. The overlap is defined as, if you look here, this is the toe of the weld. You have excess bead passing beyond the toe of the weld. So I'm going to do on the other side what we would want to see. We would want to see something like this. Actually, not even. It's hard to do a good one with this geometry, but we want something that the weld metal is fused. If you look at this here, what will happen is it'll fuse like this. It'll fuse the base metal on that angle and the bar over here. Now, there are some requirements, and I'll mention that just in a little bit, about saying to the welder, this is not acceptable. There are multiple ways to say that. The important part is quality control. Somebody needs to be following these guys before they're done with doing 2,500 roof joists and say you have to change your parameter, you have to go slower, you have to put more heat. So you're going to, instead of depositing the metal on the two surfaces, making like a caulk, this is caulking at the limit, and this is fusion welding. It happens a lot, especially when people are trying to go too fast. So the way we see it after the fact, oh, you see here how the shape is convex. If you look at it here, this piece was here at the corner, and you can see there was more material above the surface than when the toe of the weld was. So this is the overlap that I was talking about. And what you can see, this is after the fact, you can see they didn't melt that tube over here. The rectangular tube still has its original shape. You have to take my word for it. It does show a little bit of deepening because this had a galvanizing coating and a lot of paint. The painting job was perfect, but the underlying welding, the structural component, were defective. Yes?
Would you expect them to have part of the coat to do it on both sides to some extent, or is it enough to just weld it on one side?
It's a good question, and it's part of welding it on one side brings you what the structural engineer calls eccentricity. It makes the joint trying to rotate a little bit. So my main comment back to you is, when you do this design, you're assuming that it's a sound weld that can deform a little bit. As soon as your weld can deform and stretch some amount, it will be able to take the misalignment and essentially carry whatever contact force. But assuming ductility for a detail like this, where you have to throw the filler metal in a bevel in very large volume production, becomes, a question whether this is reasonable or not. So your question was really good, because when came the time to decide what to do with it, because they wanted to continue the production, the very minimum change was to weld on both sides. Just because they had so many issues, and because it was going to be repair welding, so it wasn't left as an option. Plus, it turns out they had issues with how much snow they expected to have, and the requirements up in Maine as opposed to the requirements in Holland for how to deal with snow. So things get very, very complicated quickly. So I was very happy to hear that they were going to do 2 wells. And this is, believe it or not, that project turned into enough trouble that the fabricator said, you know what, I'm going to make another batch of welded joists for free. And you're going to get them, in 3 weeks. We're working on it. We started yesterday. It still was a cost to the owner to get all the electrical out and shore the crop, because some of the crop was hanging from these joists for reason that were not acceptable. But in any event, this is a repair joist, so it's welded on both sides. And even though the factory worker knew that these were going to be subjected to that quality assurance program, because we were not involved on the first project, but on the second project we were involved to look at those joists when they came in. And you still have some joist here that has a little overlap. So if you look at the toe of the well, this is a little bit beyond, and you can tell because this is etched. So you can tell that the original bar here, the tube thickness, hasn't been melted much. There's a little bit of melting over here, a little bit of fusion. So what happened is, because the round bar, the solid bar, is much harder to heat, they had a preferential heating of that round bar so much that they didn't melt the thinner section. So you have here on the other side what they should have done. Yes?
Can you tell us a little bit more about the semi-automated manufacturing process for these things?
Okay. So regarding the semi-automated process, you have a filler wire. So you have a gun, and I have images in the first presentation, that essentially has the electrode, and you have the wire coming into it. It's a solid metal wire for this particular case, and there's also on the outside a shielding gas. So when they come, all they need to do is decide where they're going to strike the arc. You can strike it this way, you can strike it this way. The best way is to try to weave it a little bit. It's very hard in that corner to be striking all the way down. So you have to do it a little bit on one side, a little bit on the other side. And I was actually there for the qualification of some people that were doing some repair welds on site. And the best guys, that's exactly what they were doing. They're just kind of weaving it a little bit. But the gun itself is again very simple. Shielding gas, solid wire in the middle, and it feeds at a certain speed. So you can control your process. You can adjust the speed, you can adjust the voltage to a certain extent. The manufacturer makes some trade-off for you, so you only get so many options with the semi-automated processors. Okay. So in terms of deciding what's good and not good, I was talking here saying this is not good, this is good. There are some established requirement in the AWS welding code for maximum convexity. You can't be concave. This is in the fabrication section, but it's applicable in general. So if you're out there, this is one way to say, this is way too convex of a weld, or it's too small. There's some minimum sizes, a lot of limitations that you can look at. So I'll show you a good weld for this, because you can still see a lot of profiling, very small profiling, because the guy was coming on and moving a little bit. So and this was just a stick electrode, so it did have the flux and the big melted pool, and they had to clean it up after the fact. But what they were doing on site was actually the stick electrode, and they had multiple passes. So you can see one pass here that was primarily intended to weld against this, and the final pass welding on the other side. So these were actually going to be very, very strong, but it was just for temporary emergency purposes, because at the end they put on some new stuff. I ended up working on maybe 10 to 12 roof collapse projects, and I would say that at least 9 or 10 of them, the issue was the joints. And part of the issue is how people apply the welding requirement. It's written black and white, it needs to be, without lack of fusion or weld fused, but that by itself is a little general when it comes to, okay, what is acceptable and what is not acceptable. So when I was doing quality QA inspections, I started to use an ISO standard that was giving me a very specific angle between the base metal and the welded pool here for what was acceptable and not acceptable. So 90 degrees was the lowest possible level of quality, and you have close to that on some of the gym equipment. And the reason is it's thin metal and they put big welds. So it's very hard for them to weld all the base metal without putting a lot of excess material. So this is kind of gym equipment. It's still fused because this is thin as opposed to the size of the bead. And it's done very regularly. And if you go to more structural applications, that angle keeps having to go down, and it's a little bit, you can think of it as surface tension. It's a surface tension equilibrium between the bead and the base metal. The more you eat up your base metal, the more it's going to flatten out, and that bead is going to spread that way, as opposed to if this base metal is really cold, it doesn't want to wet and it stays up high on it. So there's some fundamental to explain here why you get in trouble if you trying to put too much material without heating enough this base metal. And you can change the polarity also. There's some welding processes. Flux core, you can use it in a way that you're going to heat more the base material. So it's good if you're dealing with thick sections like this. I would have done flux core. But if you're doing car components or gym equipment, then the regular MIG welding is more appropriate. Okay, so this is mostly about quality control. So I was going to talk a little bit about quality control for, I started automotive, but I actually worked more on these little sport units. So I'm going to focus on that for the next few minutes, specifically on the suspension system here. We call them A-arms because they do have an A shape, 2 long members with a cross member. And if you look at the details here, these A-arms are under tremendous forces. Here you have the whole suspension system lying in the middle of this. Here's the connection to the knuckle and then to the frame. This component gets beaten up, and it can also hit stones, logs, anything. So in terms of welding it and putting it together, the reason they use welding, again, is cost, but also accuracy and stability. If you take a bunch of tubes and you fusion weld them together on a rig in a very controlled manner, and they use robots for some of those welds, they do some manually, they do some with the robots for efficiency. When it's all done, this is the shape you're getting. There's enough metal at the junction. There won't be a bolt getting loose. There won't be any problem. You can finish it later on. So when you look at this component right here, what happened? Yeah. This went through a bunch of process of powder coating and finishing, so it won't start to rust tomorrow. It's not, if you start scratching it, eventually it will rust. But as a standalone piece, it's relatively corrosion resistant. And again, it's made precisely. It's very The control arms, if they were to start to move, you lose the stability on your unit. You lose all the